Hi, I am Anusha BM from Sri Venkateswara College of Engineering. I am going to give small presentation about applications of Schrodinger's time independent wave equation. Introduction to Schrodinger's time independent wave equation. The Schrodinger's equation is fundamental equation in quantum mechanism. It describes how the quantum state of a physical system changes over time. The time independent version of the equation is used to find the stationary states of a system. It also predicts the future behavior of a dynamic system using the wave functions in time and space. Derivation of the Schrodinger's equation. The Schrodinger equation is a linear partial differential equation that describes the wave function or a state function of a quantum mechanical system. D square xi by dx square plus 8 pi square m by h square e minus v xi equals to 0. T plus v equals to e minus h square by 8 pi square m into d square xi by dx square plus v xi equals to e xi. H equals to h by 2 pi, Planck's constant. H square is equals to h square by 4 pi square minus h square by 2m d square xi by dx square plus v xi equals to e xi. D square by dx square is equals to second derivative with respect to x. Xi is equals to Schrodinger's wave function, stationary state wave function, reduces Planck's constant h bar. Ex equals to position, E equals to total energy, V equals to potential energy, T equals to kinetic energy, minus h square by 8 pi square m d square xi by dx square is equals to kinetics energy operator. The equation does not contain time, so called time independent Schrodinger's equation. Understanding the wave function. The wave function is a mathematical function that describes the quantum state of a system. It contains all the information about the system that can be known. The time independent Schrodinger's equation is used to find the wave function of a stationary state. This is the interpretation of a wave function basic quantum chemistry. Solving a time independent Schrodinger's equation. The time independent Schrodinger's equation is the partially differential equation. It is solved by finding the eigenfunction and eigenvalues of a Hamiltonian operator. The eigenfunction represent the possible wave function of the system. The time dependent Schrodinger's equation. Here is the time dependent Schrodinger's equation. Minus d square by 2m d square xi x by dx square plus ux xi x equals to e xi x. The time dependent Schrodinger's equation is minus d square by 2m dou square xi xt by dou x square plus ux dou xi xt equals to I dou x xt by data if zo xi x is a solution to the time dependent Schrodinger's equation with energy. E show that the time dependent function xi xt equals to xi x e power minus omega t is a solution to the time dependent Schrodinger's equation if the W is chosen approximately. What is the value of a gamma? What makes xi a solution? Applications in a quantum mechanism. The time-dependent Schrodinger's equation is used to study the behavior of particles in a potential wells. It is also applied to understanding the energy levels of atoms and molecules. The equation helps in predicting the probability distribution of finding a particle in a given state. Time dependent Schrodinger's equation. The infinite square well xi x equals to root 2a sine n pi by a x e power en is equals to n square pi square h square by 2m a square. Introduction to Quantum Mechanism by David G. Griffith, second edition. Quantum tunneling. Quantum tunneling is a phenomenon where a particle can pass through a potential barrier with it classically should not be able to. The time independence Schrodinger's equation is used to calculate the probability of a tunneling. This phenomenon has important applications in electronics such as in the operation of a twin diodes. These are the quantum tunneling classification mechanism and quantum mechanisms. Particle in a box. A particle in a box is a simple quantum mechanical system consisting of a particle confined to a one-dimensional box. The time independence Schrodinger's equation is used to find the allowed energy levels of the particle in the box. The system serves as basically example of instituted quantum mechanical concept. The particle in a box, now the energy is quantized because of the boundary conditions. The wave functions are the standing waves. The more rapidly oscillating the wave function is and the more nodes is the higher the energy. This is example. Harmonic oscillator. The harmonic oscillator is another important quantum mechanical system with applications in various fields. The time independent Schrodinger's equation is used to find the energy levels and the wave functions of the harmonic oscillator. The equation helps in understanding the behavior of vibrating molecules and atomic vibrations. The quantum harmonic oscillator, the wave functions of the first three states are xi1 x is equals to a1 e power minus x square by 2b square, xi2 x is equals to a2 x by b e power minus x square by 2b square, xi3 x is equals to a3 1 minus 2 x square by b square into e power minus x square by 2b square. B is equals to root of h by omega m into omega. En is equals to n minus 1 by 2 into hw, n equals to 1 comma 2 comma 3 so on, where omega is equals to k by m whole power 1 by 2 is the classical angular frequency in the quantum number. Molecular bonding, it helps in the time independent Schrodinger's equation is used to study the bonding between atoms in molecules, understanding the formation of chemical bonds and the stability of molecules. By solving the equation, scientific can predict the properties of different chemical compounds. Minus h square by 2m that 2 xi plus Vx xi equals to E xi. Conclusion. The time independent Schrodinger's equation plays a crucial role in understanding the behavior of quantum systems. It is widely used in the various fields including quantum mechanism, chemistry and the material science. By solving the equation, researchers can make predict about the behavior of a particles and systems of the quantum level. Time independent Schrodinger's equation d square xi by dx square plus 2 m naught by h square e minus u xi equals to 0. If e is greater than u, then k is equals to root of 2 m naught e minus u by h d square xi by dx square plus k square xi is equals to 0. Xi x is equals to a sin kx plus b cos x kx equals to a e power minus e power ikx plus a e power minus k ikx. If u is greater than e, then alpha is equals to root of 2 m naught e u minus v by h d square xi by dx square minus alpha square xi equals to 0. Thank you.